Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to describe for you what is called the electric field. So what we're looking at here, I've got a pair of point charges here, Q1, Q2. Again, there's nothing special about the color red. I just like my videos to have a little color in them. I'm going to assume they're both positively charged, but it doesn't really matter if it's plus plus, plus minus, or minus minus. I'm just picking one combination for the sake of discussion. Imagine that these charges are connected rigidly to a couple of bars here, which are insulators, meaning that they're not going to let any of that charge leave this point charge. Same thing here. So imagine basically they're glued down, can't go anywhere. Now, we know by Coulomb's law there's going to be a repulsive force between these, and for right now I'm just going to focus on the force on charge 2. That force is going to be to the right. And that force will have a magnitude of K, Q1, Q2 over whatever the distance between them is squared. Now, I could draw a force vector on charge 1, but I'm not going to. I'm just going to focus here on what's happening to charge 2. Now, young Timmy here, that I like to use in some of my videos, imagine that he is observing this charge and can somehow measure this force. And a very natural thing for Timmy to ask himself is, what is it that's creating the force? What is it about this region in space that creates this force? Again, this bar here is just holding this thing fixed. So the phenomenon responsible for creating it, that's what this is all about. Timmy has to ask himself, what is it that's acting on this charge, creating this force? What is it about this region in space that creates this force on that charge? And that phenomenon is what is called the electric field. Now, when you make up a mathematical law like this, it has to be defined. So here's how the electric field is defined. The magnitude of the electric field is defined as force per unit charge, meaning that, imagine this were a 2 Coulomb charge, and imagine that we measure a force here of 10 newtons. Then the electric field strength at this location in this example would be 10 newtons divided by 2 coulombs, or in other words 5 newton per coulomb. So the electric field has a magnitude of force per unit charge, and therefore the units are newton per coulomb. Okay. Next, we got to define a direction for it, because the electric field is an example of a vector quantity. Here's how the electric field direction is defined. The direction of the electric field is defined to be the force direction on a small positive test charge. Oops, test charge. Here's what that means. If you imagine placing, this particle which is here, the force direction is to the right, and therefore the electric field vector, which would go in this point in space, would point to the right. Now, it's important to ask yourself, what is it that's creating the electric field? Well, the answer is this guy. So this guy creates what we call an electric field around it. That electric field will create a force on any charge that we place in that field. In this example, we're placing charge 2 there. And then that force will be directly away from this charge. Or if I pick another point in space, like maybe right here, the electric field at this point due to this charge would be this way. And again, I'm getting that by asking myself, if I put a positive test charge right here, what would the force direction be on it? And because it would be a plus-plus situation, the force direction would be up and right. Force direction would be up and right, and therefore that's the electric field direction at that point. If I pick a point like right here, and I imagine putting a positive charge there, this guy would repel it, so the electric field direction would be this way, and so forth. If I put a positive test charge right here, this Q1 would repel it, so the electric field direction is going to be this way, away from it. You'll notice that all these electric field vectors point away from this charge. If I put an electric field vector here, that electric field would point this way, and so forth. So basically what we would say is, all right, this charge Q1 creates an electric field around it. If we place another charge in the grasp of that field, it will create a force, and that force will be in the direction of the electric field. So kind of in the example that I'm talking about now, I'm imagining Q1 creating an electric field acting on Q2, which creates this force. It works the other way as well. Q2 creates an electric field around it. Over here at this point in space, the electric field due to Q2 is to the left, because imagine putting a test charge right here, a positive test charge. This charge would repel it, the force direction would be to the left, therefore the electric field vector at this location due to this charge is to the left. So I could draw electric field vectors around either charge. So I think what I'll do here, I'm just going to stop this video now and I'll make another video for determining electric field directions. But for now, this is how the magnitude of the electric field is defined. It's force per unit charge. And the direction is defined as the force direction on a small positive test charge, right? How you use that is you imagine a point in space, and again, let me talk about this point right here. And let's talk about the electric field due to this charge. If I put a small positive test charge right here, the force on it will be down and to the right, and therefore that is the electric field direction at this point. Now I'm gonna save the magnitude of the field, how it varies with distance and stuff, for another discussion. For now, the purpose of this video is to just introduce the electric field, and here's what it is. It's force per unit charge, and here's how its direction is defined. I hope this video helps with these concepts. Have a great day.